Good morning. My name is Rishabh Agrawal. My roll number is 4 and my batch is H1. My topic for today is weather-based crop prediction using big data analytics. The research paper that I have taken is from IEEE. It was published by senior members of IEEE from the Manipal University. This is my research paper and let's dive in. Introduction. Precision agriculture is in trend nowadays. It helps the farmers to get informed decisions about the farming strategy. Our paper focuses on collecting and analyzing both agricultural and meteorological data, including temperature, rainfall, nutrients, humidity, pH levels. And we use machine learning models to make the decisions about crops. Today in agriculture, this can allow crops to be grown at a much higher precision, enabling farmers to treat plants individually, which in turn will significantly increase the effectiveness of the output. About our data set. The dataset that I chose was from Kaggle. It has 2,200 rows of data, and it was built by augmenting datasets of rainfall, climate, and nutrients data that was publicly available. There are seven features: nitrogen, potassium, and phosphorus, temperature, humidity, pH, and rainfall. And the target is the crop, which is the name of the crop that will grow the best in the given environment. Reason for choosing this data set was that it was relevant to precision agriculture. It was specifically designed for building the predictive models that I will be showcasing today, and it was based on various critical factors such as nutrients, weather, and rainfall. Next, comprehensive agricultural data. The dataset has the key parameters essential for crop prediction, which includes the soil nutrients and the weather-related factors as well. No missing values. The dataset is pre-cleaned. There are no missing values as we will see ahead. So this saves time on pre-processing. So we can directly build and fine-tune our predictive models. Sufficient data size. As I said earlier, there are 2,200 rows. So this provides a balanced size for conducting robust analysis and avoiding overfitting. Overfitting is when the data set learns too well, it captures even the noise. So we have a sufficient data size, but it is not too large so that we even capture noise. Real world applicability, the dataset is built from real world sources, which includes the rainfall, climate, and fertilizer data specific to India. It is taken from government sources, meteorological sources. So this adds authenticity to the dataset, making our model more relevant for practical use. Next, understanding our data. Let me just run the code file. I've used Colab. So while it runs, let's go ahead. Understanding our data. Firstly, we build a heat map to see if our data has any missing values. As we can see, the map is entirely gray. There are no missing values, so we are free to move ahead. Next, we have plotted a chart of humidity against rainfall. We can clearly see from the chart that the highest humidity needed is by coconut. It is a tropical crop, therefore it needs high humidity, and that explains the massive exports from coastal areas around the country. We can also see the highest rainfall needed is by rice, and rice needs heavy rainfall approximately above 200 mm and 80% humidity. And no wonder rice production in India comes from East Coast, which has an average of 220 mm rainfall every year. This graph shows the pH value, which is best for all of these crops. We can see that a huge number of these crops are lying between the range of 6 to 7 pH. So it shows that a stability between 6 to 7 of pH is preferred for the soil. Next, the graph is rainfall against K. We can see that six of these crops are between 15 to 25 levels, which explains that if a farmer were to plant just these crops on his land, he could maximize profit uh, in this range of rainfall. This is the implementation of all the graphs I showed you. This is a Gaussian bell-shaped curve that we are getting for temperature and pH, which just reflects the Gaussian nature of these curves in real life. This graph that we have is showing the distribution of the data for our data set. It shows that all the crops have equal number of data, which just shows that the data set is balanced. If it was not, we would have to downsample some of the values. This is just a pair plot of all the features against each other. It is helpful to visualize and see trends in our data set. These are the graphs we have already seen. So let's start with our model. First, implementation. The models that we have selected, these are all classification models. We are using KNN, decision trees, random forest, and naive bias as they have been used in our research paper as well and are simple to implement. First is K nearest neighbors. The KNN algorithm is a supervised machine learning method which is employed to tackle classification and regression. It works by finding the K nearest neighbors to a data point based on a distance metric such as Euclidean distance. The class of the data point is then determined by the majority vote or average of the K neighbors. This approach allows the algorithm to adapt to different patterns and make predictions. It is a widely used machine learning algorithm, primarily used for its simplicity and ease of implementation. It is non-parametric, so it does not require assumptions about underlying data distribution, and it is less sensitive to outliers uh, compared to other algorithms, because obviously, if we take a lower k value, maybe the outlier does not lie in it, and if we take a huge k value, the outlier can get the effect of the outlier does not last as it gets divided. Um, let's see about k. K refers to the number of nearest neighbors, which is used by the algorithm. If we take case one, it means the algorithm is just classifying based on the nearest neighbor of the data point. If we take a small k, it looks at a few near neighbors, which can make the model highly sensitive to noise. Again, overfitting, as we spoke about. If we take a very large k, the algorithm will look at a large group of neighbors, which will smooth out the productions, but it will lose the local patterns, which is underfitting. So thus in practice, we need to choose an optimal K, which is chosen through techniques like cross-validation, where different values of K are tested to find the one which gives the best performance. This is exactly what we have done. As you can see from the chart, we trained our model and tested it for different values of K, and we got the highest accuracy for K equals 4. I will show this to you in our code. Um, Here. So above graph shows the ideal K value for a model is 4. It gives a KNN score of 0.9818. Moving on, decision trees. Decision tree is again a supervised learning technique. It is a tree structured classifier where the internal nodes represent the features, the branches represent decision rules. Decision nodes are used to make the decisions, whereas the leaf nodes are the output of the decisions. They will not contain further branches. The decisions or the tests are performed on the basis of the features. This is a graphical representation for getting all the possible solutions to a problem based on given conditions at each step. It is called a decision tree because, similar to a tree, it starts from the root node, expanding further branches and constructing a tree-like structure. Um, so the leaf nodes would be the names of the crops, and the decisions would be made based on features such as rainfall more or below a certain level, etc. Feature importance. Feature importance is a technique used to rank the input features by their relevant importance in predicting the target variable. So at each node, the algorithm will select a feature which is best splitting the data into subsets, maximizing the homogeneity of the target variable within each dataset. The chosen feature is the one which significantly reduces the impurity metric, such as a Gini impurity. The importance of features based on how the error is reduced by splitting on that particular feature, weighted by the number of samples that pass through the split. So for we can see through the graph that rainfall is the most important feature in our graph, followed by humidity and etc. So maybe the root node would be rainfall, and then we would split based on that, uh, and so on. Next, random forest. Random forest is an extension of decision trees. It is widely used for classification. It creates a number of decision trees. Each tree is constructed using a random subset of data to introduce randomness to the algorithm, which reduces the risk of overfitting, which was a huge problem as we saw earlier. So this will improve the overall prediction performance. The algorithm will then aggregate the results of all the trees, either by voting or by averaging, and this collaborative decision-making process, supported by multiple trees, provides precise results. The diagram you can see there are multiple decision trees, and their outputs will be averaged using voting. This image shows the classification report for a random forest classifier. We talk about precision, recall, F1 score, and support. Precision is the proportion of correctly predicted positive instances out of all instances that were predicted as positive. So, for example, for Blackgram, it is 0.778, which means 70, 7 out of 100 Blackgram predictions are correct. Recall. Recall is the proportion of correctly predicted positive instances out of all positive instances for each class. So it measures how well the model identifies all true instances of the class. Mothbean has a recall of 0.655, meaning out of all actual Mothbean instances, it will correctly identify about 65.5%. F1 score is the harmonic mean of precision and recall. It gives a perfect balanced view of precision and recall. Perfect score is one, lower the score, worse the performance of class. Support is the actual number of instances for the class, indicating how many examples of each crop are present in the dataset. For example, watermelon has 25, while apple has 24. Naive Bayes. These are correction of classification algorithms, which are based on the well-known Bayes algorithm. It is not a single algorithm, but a family of algorithms where there's a common principle that every pair of features is independent of each other. You can see the Bayes theorem stated down. P of C given X is P of X given C into P of C upon P of X. This model predicts the probability of an instance belonging to a class with a given set of feature value. It is a probabilistic classifier because it is assuming that feature in the model is independent of another feature. So in other words, each feature contributes with no relation between each other. Next, in this chart, you can see each feature's mean value represents the central tendency of that feature for each crop, allowing us to understand how different crops are characterized by their nutrient and environmental conditions. The bar plot visualizes these mean values, allowing us to compare how different crops differ based on their features. Feature variability. If two crops have very similar mean values for a feature, it can be challenging for the naive Bayes classifier to distinguish between them based on that feature. And feature importance is that if features are showing a significant difference in mean values across classes, obviously the Bayes classifier will be like those features will be more informative for classification. This is the implementation for all four models. You can see we get the accuracy values for all four of them. And then using those values, we can make a comparison chart right here. In the chart, we see that the highest accuracy that we're getting is for naive Bayes, followed by decision tree, KNN, and random forest. Now as we see that we got the highest accuracy for naive Bayes, we can use that for crop prediction. I have taken a data value right from our dataset itself, the first value. I input it, I predict it using the naive Bayes model, and the predicted crop we get is rice, uh, which is correct, as you can see, correctly identified. Thank you.